let's start off. So today, in section 4.2, we're going to estimate the sine, the cosine of any number, and we're going to be referring to the definitions. So here it does ask me to give the exact value. So we're not saying approximately, divide something and give me a decimal equivalent. What we are saying is keep it as a fraction and don't simplify things further. So after we do Pythagorean theorem here, we get the square root of 39. So now the sine of theta is going to be the opposite radical 39 over hypotenuse, which is 8 there. So the tangent of A, TOA, is opposite over adjacent. So we're still going to use this number right here, radical 39 over 5. And lastly, we're going to say 5 over 8 for the cosine there. So we do not need to convert to decimals at all. The moment you convert this to a decimal is the moment it's not exact anymore. This one, you can convert to a decimal, and it will be exact because the 8 is ends. It's not a repeating. Same thing applies over here. Pythagorean triple, 3, 4, 5, and then we just have our ratios here. If we did convert these to decimal, it would stay exact. So we can do that. But generally speaking, we'll leave it as a decimal there, or excuse me, as a fraction. So the unit circle. The unit circle derives itself from trigonometric ratios, not entirely, well, we're going to look at just quadrant 1, just to give you a heads up. This is quadrant 1 right here. We go counterclockwise. If you're British, you would go anti-clockwise. So 1, 2, 3, and here is quadrant 4. Each quadrant has certain characteristics about the numbers that live in them, and we're going to look at that later in this lesson. But first off, let's talk about what the unit circle is. First off, the unit circle is a circle that has a center at the origin, also known as 0, 0, and it has a radius of 1. For you non-polyglots, that means 1, and of course, that's where we get the name unit, because unit means 1. So the radius from here to any point on the circle is 1. So all the way, the spokes of that wheel, each of them would be 1. 1 whatever, 1 unit. So if the point starts here, this is our initial point right here. So that point is 1, 0. And the idea of the unit circle is what we're doing is just taking that point and we're going to swing it around, woo, woo, like orbit, just around the center like that. So if the point starts at 1, 1, then the segment from the origin, so this segment right there, it has a measure of 0 degrees, also known as 0 radians. Okay? As the point rotates, so let's just say the point rotates, and now is located here. Doesn't matter where you place that point. We call that a rotation theta, so r sub theta there, because it now creates this new segment. It's almost like the segment, as it rotates, the point rotates, this segment just opens up, or the angle opens up. So the segment makes a larger angle until it reaches all the way around, and then it just repeats, okay? So when it reaches 360 degrees slash 2 pi radian, as that point goes around, it'll just repeat all over again. That doesn't mean there's not repeating. There is some sort of repeating that happens also inside here as it goes, but the entire cycle will go through again. So notice that no matter where I put the point, so let's say I just put the point here. Notice what's created. what's created is a triangle, and more specifically, a right triangle. And as we look at that right triangle, this has a length of something like A. This has a length of something like B, which means this point right there is at the location AB. So let's see how that's important. Looking at the triangle over here, we're just going to look at what's called a reference triangle here. I just extracted any old triangle from there. And we're going to use this here. Now remember that this is a point right here. This is a coordinate, AB, like so. And we already know that this side...
Wait, why is the top point AB and not the bottom right?
So the question is, why is this point AB and not this, not down here?
Yeah.
Because if I take this point out here and I rotate it around to somewhere here or here, it doesn't matter where, notice it drops down. And so now this point, which corresponds to that, is just somewhere inside the circle. The only point that's on the circle is this one here. This one here. This is on the circle, so this reference triangle, that's on the circle. Okay, so now we have this reference triangle, and let's talk about the ratios. So we're calling SOHCAHTOA, and specifically we'll look at sine and cosine. I'll start with cosine. So the cosine of theta is, if we look at this, cosine of theta is not opposite, but adjacent over 1. Therefore, the cosine is just A. Let's continue. The sine of theta is opposite B over hypotenuse, which is also 1. So therefore, the sine of theta is simply B. So what do we notice here? This point, which is AB, is actually the cosine and the sine of this angle, whatever it is. Whatever angle is here. The statement was said, if we have this coordinate right here, can we find this angle? We certainly can, because we know what the cosine is, we know what the sine is. So we would just have to do the inverses to find out what that is. But let's now officially define cosine and sine relative to the unit circle. For all real numbers theta, the cosine of theta and the sine of theta is the image of the point 1, 0 under the rotation of theta about the origin. That is, cosine of theta and sine of theta, comma, sine of theta, is equal to just that point being rotated. So, as we do this, wherever we rotate it, let's just pretend I rotate to here. This height right there is my sine. And this x value is my cosine. Wherever this blue one rotates to, so as it goes around, this just represents the sine and cosine. Now, some of us will say, wait, this is odd to me because we're writing cosine first, and we're used to saying sine first, sine, cosine, and tangent. Just recall that this is alphabetical, if that helps you remember. Alphabetical, cosine comes first and then sine. Cosine comes first, then sine. Just like x comes first and then y. So if that helps you, cosine is first and sine is second. X is first, y is second. So on the next page, let's look at example number 1. And we're going to try to evaluate using our graphic down there. So on the unit circle, cosine of pi and sine of pi. Now, since it does say pi, folks, we know that radians is being used here. And if we recall where pi is, where 2 pi is, etc., so watch this. Remember that this here represents 0 degrees, also known as 0 radians. This point right here is at 90 degrees, also known as pi over 2 radians. And this point right here represents 180 degrees, which is pi radians. While we're here, let's go ahead and finish up the last one down there. This one here is 270 degrees, 3/4 of a revolution, which is 3 pi over 2. So the question here is, on the unit circle, what is the cosine of pi? Well, that means we're talking about this point right here. So what's that point? If you recall what that point is -1, 0. So, since the point is -1, 0, what is the cosine? That means the cosine of pi is -1. And the sine of pi is 0. Because that's the cosine and that's the sine. It asks us to check with the calculator, so just pull out your handy-dandy calculator and punch it in. The next part of the instructions, now let's add the quarters to the units. We already did that, but let's actually add the specific point. This point here is 0, 1, which means if you were to interpret this as a sentence, the cosine of 90 degrees is 0. The sine of 90 degrees is 1. Which means this point down here is 0, -1. And to interpret that as a sentence, the cosine of 270 is 0, and the sine of 270 would therefore be -1. It's just the coordinates of each point as it rotates around. Now, these ones are nice and pretty. The ones that get inside are a little bit more complicated, and we're only going to look at a few of them on each side. And that's going to be the extent of the unit circle, and we're going to cover that by the time we get to section 4.4. So we're going to build on this for the next bit. We'll show you that there's a really nice pattern, so you don't have to think too hard. You just set up the pattern and do it. And then you can evaluate sine and cosine and tangent for a lot of the basic angles. 60 degrees, 30 degrees, 45, 135, etc. Let's continue on and take a gander at tangent. The question earlier was asked, well, what's tangent? How is tangent represented on this? Well, let's look back at my reference triangle. If this is my theta, and this is my coordinate, AB, that means tangent, as we recollect, of something is opposite over adjacent. In this context, it is opposite is B over A is my adjacent. And we already know what those represent. This is my sine of theta over my cosine of theta. Because B simply represents the sine and A represents the cosine. So there actually is a definition. We now have a definition for tangent of theta. So here's my definition. For all real numbers theta, provided that cosine of theta is not 0, then the tangent of theta is simply sine of theta over cosine of theta. If cosine does equal 0, notice putting 0 down underneath, we just say that tangent of theta is undefined. So in other words, tangent of theta, if you can recollect, go back to Algebra 1. What if I said y over x? What would you call that? Y over x. Do you remember that? Y over x. Give you a hint, starts with an M.
Slope.
My slope. Good, so here's what tangent represents. In other words, tangent of theta is the slope of the segment to the point. Is it a steep slope or not? Is it a shallow? I do want to give you a hint also what to not confuse this with. Don't confuse this with tangent of a circle. If you recall from your geometry days, if you have a circle and, for example, a wheel touching the ground, the wheel touching the ground, this line right here is called a tangent line because it touches the circle in exactly one place. But it doesn't have to be that. I could have a ladder leaning up against a sewage thing or whatever, a pipe. That would be tangent also. So there is a slight relationship between this concept of tangent and the tangent inside here. For example, right here, if I drew the tangent there, and this is my slope represented here, essentially they're perpendicular. So there is an interesting idea about the tangent of the circle relative to the tangent of the unit circle. So anyways, we don't want to confuse you. Let's leave it at that. So using the tangent circle, so we don't even need to use our calculator, what is the sine of 270? Well, let's recollect. 270 is down here, and the sine is the second part. So the answer is -1. The cosine is 0, and the tangent is just the sine divided by that, so we say it's undefined. Notice my first example used degrees. The second example uses radians. So take a moment now to do part 2 and part 3. Go. So on page 3 here, let me guide you through what we're going to do. Number 1, we're going to label the point A, which is at 1, 1, or 1, 0. So here's A. Then we're going to take our protractor so that we can rotate this 50 degrees along that. So remember how we set up our protractor. We bring it over here. We line everything up. Make sure that this here has to go on the center, and this line has to line up with that, as does this here. So here we see it pretty well lined up down there. This looks like the crosshairs go, lines up there, lines up there. So now we need to go to 50 degrees. We're using the inside. 50 degrees is there, which means it's going to match up right here at the 30. Or 130, excuse me, because 50 corresponds there. And if we were to make our protractor larger, like so, now we see where our point is. So this point right there. So let's move our protractor out of the way. And now we see our point. So let's find out what our coordinates are. If we were to bring this down and find out what the x-coordinate is here, the x-coordinate is approximately 0.65. And our y-coordinate is approximately here at 0.75. So that helps us answer the question, what is the approximate value of the cosine? So 0.65. What's the approximate value of the sine of 50 is 0.75. And we can just put that into our ratio, 0.75 over 0.65. And that'll work, but we could also go a little bit further by simplifying that. Now repeat that process for the rest of these. We're going to do, notice here you're using the calculator, and now we're going 155. Do notice that there is a slight error here. We're rotating 155, which means each one of these needs to be changed. Like so. And of course, you are going to be checking with your calculator too to see that you are accurate. The next part, taken from our book, is we simply have a starfish overlaid here onto the unit circle. So suppose the tips of the arms of a starfish determine the vertices of a regular pentagon, congruent sides, congruent angles. The point A is at 1, 0, right here, and that's the tip of one of the arms. And so one vertex of a regular pentagon, A, B, C, D, and E, is inscribed into the unit circle, as shown here down below. So we're going to find the coordinates of B to the nearest thousandths. So see what we can do. Now, of course, on this grid, we don't have enough accuracy to do it, but here's B, and so my X value is right down there, and my height, my Y value is right there. So what we need to do is plug that into our calculators to figure out what it is there. So what's the angle? What's the theta that we need here? So what is this theta? Well, remember, this is a pentagon, which means it has 5 sides. So we're going to take 360 degrees and divide by 5 to get 72 degrees each. So if I were to say, well, what are my coordinates there? The coordinates are just the cosine of 72 degrees and the sine of 72 degrees. So all I have to do is evaluate that with my calculator. And here I get 0.309, which makes sense because this is about 1/3 of the way across to here. And the next one is 0.951, which makes sense because it's rather high, almost all the way up to the unit there. And that's a 951, which I used my calculator. Now you're going to finish this one up, example 4, just find out what each one of those are. However, note we don't actually need to use our calculator. Why not? The hint being here is that everything in quadrant 1 is positive. Everything here in quadrant 2 is a negative then a positive. Over here in quadrant 3, we have a negative and a negative. And lastly, we have a positive and a negative. So use this information to actually note things that are similar heights or things are just switched around. So think about that real quick before you plug things into your calculator there. And the last bit here, on your own, go ahead and use the unit circle right here to approximately find what letter each one of these corresponds to on this unit circle.